My name is Daniel. I will introduce this project. So the main purpose of this project is that as the project manager at SHANG Group Power Supply, there is responsibility to oversee and actively engage the design team in testing a complex power supply circuit. We need to transform the alternating current voltage into the stable and regulate direct current voltage. So the proper emphasize the application of theoretical knowledge to real-world situation, highlighting the need for a comprehensive understanding of electrical and electronic principles. So the ultimate goal is to modify the performance of the power supply circuit before proceeds with production on a large scale. So for the methodology, we are using multi-sim simulation software. The approach integrates theoretical principle with practical simulation covering the setup, analysis, and comparison step. It emphasizes the consideration of each component properties including transformer, diode, capacitor, and IC regulator. The validation process involves comparing theoretical formula with simulate result at various stages of the circuit, ensuring alignment and accurate. The perform measurement waveform and precise correlation with theoretical expectation is crucial for consistency. The overall goal is to systematically validate the accuracy of the power supply circuit.
Hello, my name is Bryan, and now I'll be presenting the simulation results. So our group was given set A, which has the LM7805 and LM7905 voltage regulators, and which has an expected output of 5 volts and negative 5 volts respectively. We ran a simulation using multi-sim software to check if the power supply circuit for both of the regulators work properly. So the goal is to make sure the circuit functions well before mass producing them for the market. So the circuit produces a typical output of 240 VRMS at 50 Hz from the AC source. It includes a 10-1-1 transformer, 1 N402G diodes, and a set of electrolytic capacitors for the regular inputs and outputs as shown in the next slide. So this is the overview of our circuit.
In the figure shows sinusoid waveform of the transformer at input and output terminal. The input is green in color while the output is represented in purple color. The input voltage has a peak value of 339.133 while at the output port, the peak voltage is 33.913. The difference of the input and output voltage source is due to the application of step-down transformer where the input is set down to 1/10 its original value to 33.913.
Next, we'll be going through the result for the IC regulators. As you can see from the screenshot, we found that input voltages for LM7805 and LM7905 were 33.159 volts and negative 33.177 volts. Typically, according to the spec we have researched, LM7805 should handle between 7 volts to 25 volts positive for both, and LM7905 should work with negative voltage between negative 25 volts to negative 7 volts. So initially this measure value seemed too high, indicating a possible problem with the circuit and the input. However, after further research and considering the absolute maximum input voltage, limits of 35 volts and negative 35 volts were found on the internet, and according to some product spec sheet, we found that these values are actually okay within the updated constraints. This highlights how crucial it is to stay informed about the components specification for accurate simulation interpretation.
Regarding the output voltages, we got 5.01V for LM7X05 and negative 5.683V for LM7905. Ideally, LM7X05 should give positive 5V and LM7905 should give negative 5V. The 5.01V for LM7X05 is quite close to the expected value and generally acceptable. However, the negative 5.683V for LM7905 is beyond the maximum tolerance of 5%, which is negative 5.05V. This suggests a need for a closer look at the separator circuits, considering factors like layouts or simulator model accuracy that might cause these differences. In summary, theoretical ideas and actual measurements tell us how well the power supplier circuit is working. Some things match what we expected, but the differences in output voltages show area where we can make things better. Teamwork, careful circuit analysis, and adjusting parameters precisely are important before starting mass production. Continuously refining the circuit based on simulator results is essential for creating a strong and reliable power.
Next is company aim to revolutionize its production processes by integrating sustainable and innovative power supply solutions. The company seeks design that not only meet technical requirements but also align with its sustainability goals. Therefore, your group must engage in a collaborative thinking process to present a solution, taking into account the following criteria. First is creative solution. Exploit innovative power supply design beyond conventional circuit. Propose an energy harvesting power system utilizing piezoelectric, thermoelectric, or solar technology to reduce reliance on external sources. Advocate for a hybrid renewable energy system integrating solar, wind, and energy storage for a resilient, eco-friendly solution. Suggest a distributed power architecture, decentralizing conversion processes within a facility to optimize energy delivery. Last, consider incorporating thermal energy harvesting using thermoelectric generator to convert waste heat into electricity, showcasing resource optimization for energy sustainability. Second, advantage and challenges. The innovative power supply design such as energy harvesting, hybrid renewable energy system, distributed power architecture, and also the thermal energy harvesting offer distinct advantage for improving energy efficiency and reduce waste in production processes. This design aims to optimize power conversion, enhance the distribution mechanism, and utilize energy effectively within a facility. Additionally, the integration of renewable energy sources like solar and wind not only contributed to a diversified energy portfolio but also reduce reliance on finite and polluting non-renewable options, fostering an eco-friendly and resilient production process. The third one is eco-friendly component. To compare the environmental impact of traditional power supply cycles with innovative, eco-friendly design is crucial for informed decision-making in sustainable practice. Traditional cycles often use materials like silicon with significant environmental impact and energy-intensive manufacturing processes. In contrast, eco-friendly design explores alternative materials such as organic electronic and recyclable components, aiming to reduce the environmental impact of manufacturing. Additionally, innovative proposals enhances sustainable manufacturing processes, contributing to lower pollution and carbon emissions. The consideration of end-of-life factors like recyclability and biodegradability align with a circular economy, promoting responsible resource use, and minimizing waste. And the last one is sustainability assessment. The proposed power supply design offers long-term sustainability benefit for the manufacturing company include significant reduction in the carbon footprint through the integration of renewable energy sources, energy efficient components, and also the innovative power management system. The adoption of renewable energy not only enhances energy resilience but also aligns with global targets for increasing the share of renewable energy. The design further aligns with United Nations Sustainable Development Goals, particularly those related to affordable and clean energy, responsible consumption and the production, and the climate action. Besides, the design contributes to addressing the global issues of electronic waste by incorporating recyclable material and modular design, aligning with efforts to reduce the environmental impact.
Thank you, Sanjin. My name is AMIRAH. Now my part is end-of-life consideration. Explain how the proposed design address end-of-life consideration for the power supply components. Proposed energy for the recycle of disposing of component to minimize environmental impact. It is critical to follow the proposed end-of-life procedure when a power resource purpose the end of useful life in order to reduce environmental effect and advance sustainability, restoring the energy supply and recording material to the method of recycling and disposal of pipe to reduce their negative effect on the environment. In elemental strategy, identify potential challenges implementing innovative design within the manufacturing process. Purpose strategy to overcome the challenges we ensure seamless integrations. To regarding creativity design and product technician in industry manufacturing business mean has the highest qualified personnel. This may be too complex by hearing resource needs personnel forming analysis which academic institution and implementing training and development initiative. Last, cost benefits analysis. Record a cost benefit analysis comparing the internal investment and cooperation costs of traditional and innovation design. Discuss how the long-term benefit of sustainability offset internal costs. The main idea for lower start-up expenses to encourage participants to outline below. This might lower in upfront cost as compared with implementing green initiative, enabling a legal market share in the integrated electric wireless industry. Thank you for the watching.
In conclusion, the validation of a power supply circuit design for LM 7805 and LM 7907 voltage regulator using multi-sim simulation software provide valuable insight into its functionality. The project manager at SHANG Global Power Supply emphasized the responsibility to oversee the testing of the complex power supply circuit before mass production. The simulation result confirmed successful voltage set down and accurate transformer performance. However, deviation in output voltage from the IC regulator prompt consideration for enhancement and adjustment in the circuit configuration. The conclusion highlights the importance of effective collaboration, analyze and persist adjustment for optimizing performance and emphasize the evolving nature of electrical and electronic engineering, requiring constant refinement and adaptation for dependable and precise electronic circuit.